I know you've heard a little bit about Samplematic and the Executor throughout the week, but it's my pleasure now to introduce them in greater detail and describe many of the concepts that are embedded within them. So here's the timeline again that Tushar showed. And right now we'll be focusing on phase 3, where we introduce 3 new tools: the Samplematic Python library, the new Executor primitive, and an iteration of the Noise Learner service. And together, these will enable sort of a dramatic transformation in the transparency and local introspectability of mitigation workflows. Okay, so I think it's very important to take a step back and look at this very fundamental building block of many randomization-based quantum error mitigation methods. And this basic building block is called addressed layer. Now, addressed layer has 2 parts. The first part is typically a round of simultaneous entangling gates, in this case, CZ operations. The second part is what we call the dressing. The dressing, in this example, consists of 3 parametric gates on each of the qubits. You know, sometimes you have more gates, sometimes you throw in some static gates too, but the point is that with these 3 parameter values on each of the qubits, you have enough expressive power to implement any single qubit unitary on each of those qubits. And at execution time, the parameter or the angles that you plug into these parameter values are typically the composition of a couple of things. So they're the composition of the user gates that come from the application circuit, but they're also composed and expressed in these parameter values are the random gates that come from certain mitigation methods. Now, why are addressed layers such an important concept in these mitigation workflows? It's because they define a portable noise context, right? So the addressed layer and its randomizations appear identically in both the learning circuits and the application circuits. And this is what gives you the strong confidence that you're dealing with the noise models you think you're dealing with when you're trying to apply error mitigation. And so you want this concept to be portable between your learning and your application. I used the word randomization and twirling a couple of times in the previous slide. So I should also explain a little bit how those concepts fit into this dressed layer definition, right? So here I have a picture of a dressed layer in the middle. And what we want to do in sort of the canonical twirling case, which is Pauli twirling, is we want to sandwich our entangling layer with random n-qubit Paulis. But we want to do this in a way so that we don't actually change the logical nature of the circuit. So we choose a random Pauli, we put it on one side, and then we choose another random Pauli on the other side, which cancels the other one out because they can propagate through the Clifford layer effectively. So Samplematic actually thinks about twirling in similar but slightly different conceptualization. So instead of thinking about twirling as a sandwich of random Pauli gates for Pauli twirling, it actually thinks about it in terms of a single twirling event that happens at some very specific place in your circuit, denoted by this star and this dashed line here. So at this twirling event, we choose a random n-qubit Pauli, and we virtually place it and its adjoint into the circuit at that moment in time. And so we've effectively done nothing. And then we can imagine that the Pauli and its adjoint travel through the circuit, leftwards and rightwards. And they travel until they hit a dressing, which is willing to absorb them. So you can see here that the leftward traveling Pauli it needs to be propagated past that layer of 2 qubit gates, and then it's going to be absorbed into that dressing. And then its adjoint is actually going to end up in the adjacent dressed cycle in this example. And of course, this is happening, in this picture where we have lots of dressed cycles. This is happening in this example for every dressed cycle. And so, in general, every dressing will get random Paulis from its neighbor and from itself. There are other kinds of randomization events you can consider. So imagine that you have a cache of noise models, which describes your belief about the noise processes of dressed layers inside your application circuit. So at execution time, you might be interested in injecting noise into your circuit to do error amplification, or you might be interested in injecting anti-noise into your circuit to do some sort of runtime error cancellation. And so this is a single-sided emission event. Unlike twirling, we don't have a two-sided emission event. We have a single-sided where we're injecting a Pauli, and this can be combined with other randomization events like twirling. All right, so this is the suggested workflow that we have for you with the Samplematic and Executor and NoiseLearner v3 integration. So we're going to declare your intent of how you want to exactly randomize your circuit and implement your mitigation protocols or your noise tailoring protocols. You're going to learn your noise models if you need them. Then you're going to build your declarations into a procedural representation of randomization, and you're going to do this locally on your own computer so that you can introspect the process. You're going to upload your processes to the runtime environment where they're going to be executed concurrently with execution on the QPU. And then finally, your job's going to be done and you will have some results to process. Samplematic is a Python package that we are going to need for this workflow example. It's open source, it's vendor agnostic, and you can pip install it today. And what I want to emphasize about it is that it's a general extensible framework. So we are going to describe some of its features today, but we don't expect those features to stay static. We expect to extend them. And in particular, we want your feedback and support in choosing how to extend them. So here's the first step of our workflow, declaration. Qiskit 2.1 introduced a new instruction to the quantum circuit called a box. A box is just a local scope inside the quantum circuit, and into a box you can put any other instruction or set of instructions. In this case, I've made a very simple toy circuit with 2 boxes. What you can also do to boxes is you can give them 0 or more annotations. The Samplematic Python package defines a few annotations. And so in this example, we have given both of our boxes the twirl annotation, which is a declaration that, it's advancing. It's a declaration at execution time, we would like these things to be twirled, the contents of these boxes to be twirled. Into the first box, I've put some single qubit gates, which will be folded into the dressing. I've put some 2 qubit gates that I want to Pauli twirl. And I'm also interested in doing measurement twirling because I've wrapped my measurements inside of a twirled box. Currently, we have 3 annotations. We have the twirl annotation that was on the previous slide. We have an inject noise annotation, which declares that you would like to, at execution time, inject some sort of stochastic Pauli model into your box. And we have a change basis annotation, which means that at execution time, you would like to go into or out of the canonical basis into a basis of one of the eigenstates for that qubit. I won't be talking so much about the second 2 annotations in this talk. I'll leave it to the subsequent talk that Max is going to give. Each of these annotations has some configuration options. So for example, with the twirl annotation, you can specify the group, although right now you're limited to just the Pauli group, though we plan to extend that. You can choose whether you want your dressing layers to appear on the left-hand side or the right-hand side of the box. And you can specify one of 2 decomposition modes for your dressing. So currently with RZ, RX gates or RZ and SX gates. And again, this is extensible, so we can add new decomposition methods as we need them. Annotations are also not mutually exclusive. So in this example, we're adding all 3 of the annotations to a single box, which is a declaration that we want to do all of these things at the same time. The build method will raise an error if you try to do things that are mutually incompatible. And so far, we've been focusing on drawing your boxes manually, right? So this would be a very manual workflow, which is sometimes helpful, but sometimes maybe perhaps you do not want to draw your own boxes. And for that reason, Samplematic comes shipped with a pass manager, where you can take any circuit and you can give it to the pass manager, and it will output a boxed up circuit. And it's configurable, so you can say things like, I do want to do measurement twirling, or I don't want to do measurement twirling, and it will set the annotations according to that configuration. Okay, so we've made our declarations with the annotations that live on our quantum circuit. And if we have decided to inject noise, then we ought to have some noise models kicking around. And for this purpose, we have designed, an iteration of the existing noise learner service. So a little bit more than a year ago, we introduced a noise learner. And this is an iteration of it with a couple of key upgrades. The first is that it was designed to be compatible with this Samplematic executor workflow, and it does that by making the input just a sequence of boxes, whereas the old input was some circuits and it chose stratification for you behind the scenes. The output of the new noise learner is a sequence of noise models, one noise model for every box that you give it. The other big difference with the new noise learner is that you can give it boxes that contain measurement instructions, and it will give you noise models of those boxes. Max will be talking more about this. I'm going to go to step 3, which is the build method. And it's important to note here that so far, we have not actually done any randomization whatsoever. We have only declared our intent to randomize, right? So we need to move from that. And for that purpose, what we do is we invoke the build function in the Samplematic library. And this is like an interpreter. It takes your declarative model of randomization, and it interprets it into a procedural representation of twirling. And it does this by accepting as input a boxed up circuit and outputting a two-tuple. The first element of the two-tuple is what we call the template circuit. This is just another Qiskit quantum circuit object. The second element of the two-tuple is a samplex object. A samplex is the main type defined inside the Samplematic repository. Let's start with the template circuit. So on the left here, we have our boxed up circuit. And on the right, we have our template circuit. And we can see that there's a very simple correspondence between the groups of instructions that we chose to box up and what appears inside of the template circuit. If we zoom in on, say, the second box, we can see that because we've specified the decomposition mode as RZ, RX literal, we end up with 3 parametric cubic gates with unique parameters that are able to express the single cubic gates that we need to be able to fold into that dressing. In particular, you'll notice that this box also has a square root of x operation on the first qubit. This is not present in the template circuit. This is present in the samplex, and it's the samplex's responsibility to remember this SX gate and fold it into the randomization at sample time. Okay, now let's talk about the samplex object. What is the samplex object? And I want to be clear that users of Samplematic in this workflow don't actually need to know what a samplex is or how it works. They just need to pass them around. But since this is a developer conference, I think it's maybe worthwhile poking in there and seeing what it's like, right? So it's a graph representation. And it represents the process of randomization. It doesn't represent the samples of randomization. It represents the process of randomization. Of randomizing parameter values that are valid for the template circuit, and also classical values that are required for post-processing. If you're measurement twirling, you've inserted random X gates before your measurements, and you need to remember what you put in there so that when you're post-processing, you can flip them back to their correct values. And a samplex graph has 3 categories of nodes. It has these star-shaped nodes, which are responsible for instantiating what Samplematic calls virtual registers. Virtual registers are a key idea inside of the Samplematic package, and they are arrays of gates that the sampling process needs to reason about as it randomizes. The second category of node inside of the samplex graph are these green circles, which are mutations of existing virtual registers, right? And virtual registers actually have a type system. So there are different types of virtual registers that you can have. There are poly virtual registers, there are 2x2 unitary virtual registers, there will be Clifford virtual registers, and you can sort of cast one into the other if appropriate. And so these green circles are doing things like slicing virtual registers, casting virtual registers, propagating virtual registers, and so forth. The third category of node are these bow ties. These are responsible for looking at the final state of all of the virtual registers and synthesizing them into the output tensors that the user receives at the end of the sampling process. Let's walk through a simple example where we again take our toy circuit with two boxes that has been built with the build function into the template circuit at the bottom left and the Samplex graph on the right. And let us see how this Samplex graph and this template circuit interact with each other in the sampling procedure, right? And just as a reminder, our little toy circuit has two boxes. In the first box, we have our two entangling gates, and we also have our parametric RX gates. And in our second box, we're performing measurement twirling. So let's start somewhere in the graph, right? So we need to walk the graph. So the star that we're pointing at corresponds to a sampling event at this moment in the template circuit. And so we're going to instantiate two virtual registers with the same random Pauli. And we're going to send one left and one right in the sampling graph. Then we look into the next node. This is a slice register node. This node is actually not very interesting. But at times we have virtual registers and we need to sort of permute their order or take slices of them because the next nodes inside the graph need to operate on only a subset of them or something like that. The next node in the graph is slightly more interesting. This node is called a poly-passed Clifford node, so it does exactly that. So this node is responsible for taking that particular virtual register and mutating it by passing it through the CZs that are present in our circuit. And now we need to deal with these two parametric RX gates that were in our base circuit. And these two gates only appear on 2 of our 4 qubits, on qubits 0 and 3. So we need a slice node that is taking a slice of the 0th qubit and the 2nd qubit because the next node is responsible for doing a right multiplication against the values of those RX gates. And then finally, we have something different has happened on qubits 0 and 2 and qubits 1 and 3. And so we have a combined registers nodes, which is stitching 2 virtual registers together and creating one effective virtual register, which the final node is going to act on. And this bow tie node is responsible for taking the value of that 4-qubit virtual register and synthesizing it into angles that are valid against this chunk of the template circuit. Now, we've only looked at one leg of the sampling graph. We can introspect all the nodes in the same way. So for example, we ignored this rightwards traveling Pauli. That's accounted for by this node number 10. And then this bow tie node over here, the dark blue one, that's responsible for synthesizing angle values for our second block of parameter values. And then of course, since we're doing measurement twirling, we also need to account for this. So we have this second sampling event, which is responsible for randomizing the measurements. And so we need to send our virtual polys leftwards to get incorporated into this dressing of the second box. And we also need to send it rightwards so that this third bow tie operation is taking those values and returning them as bit values so you can incorporate them in your bit flip post-processing. Okay, so we've walked through the Samplex. Now, how do we use it? A Samplex object has a sample method, and in many ways, the sample method is strongly typed with tensor values. So it has a tensor IO model. And so if you just print out the Samplex, it's going to tell you exactly what you need to input into the sample method to make it sample, and it's going to tell you exactly what it's going to output when you request samples. It's going to tell you the names of the things it's going to sample, the shapes of the tensors it's going to sample, and the types of the tensors it's going to sample. So in this example, our SampleX happens to have 27 nodes, and as input to the sample method, it requires 3 named tensors. The first tensor in this example is specifying basis changes as an array, and it needs to be an array of 1 dimension with 4 elements. It also needs as input parameter values to the parametric Rx gates that were in our circuit, and so we need 2 parameter values. It also needs as input a noise model because we were doing some noise injection in whatever example this is specifying. It also tells you what you're going to get as output. So for example, it tells you that you're going to get some parameter values, and these parameter values will be valid against the template circuit that is paired with the SampleX object. Right, so this is how you invoke the SampleX. It has a method called sample, and you just call it. Right, so here we're saying output equals samplex.sample, and we need to give it all of the tensors that it requires. So we need to specify what are the input parameter values, 0.1 and 0.2. What are the input basis changes, these specifiers? What is the noise model, this noise model? And then we request 123 randomizations, and what we get out of the sample method is a mapping object that has all of the tensors that it guarantees to return. So for example, we get a parameter values array which has shape 123 by however many parameters happen to be in the template circuit. So every row of this is a different randomization. We also get outputs for the classical post-processing tensors that we need. So we get an output array called measurement flips.meas, which corresponds to the bit values that we need to correct our measurement flips with. And what I really want to emphasize is that all of this is happening locally, client side, on your laptop, and you can introspect the thing. You can see exactly how it's going to sample before you choose to execute. So just as a simple example, I've thrown together a 3-qubit circuit, right, called circuit, and I've plugged it into qiskit.quantuminfo.operator to get an array representation of the unitary that the circuit implements, and I've drawn the absolute values of that unitary on the right there. Now, if, for example, I was for some reason not trusting the SampleX that was actually doing Pauli twirling, or that it was doing something incorrect, I can take my template circuit and I can assign it the parameter values as output by the randomization process, right? So I'm taking the first row of my angle values and I'm assigning it to my template, and then I'm casting that to a unitary, and I can see that for all 3 of these randomizations, I'm getting a picture that looks exactly like my base circuit. So I have some trust that it's actually twirling properly. Right? This is a very simple example. If you have noise injection, you can scale down your thing, you can do a full simulation, and you can check that it's injecting noise in the way that you expect it's injecting noise before doing any execution whatsoever. Which brings us to execution. So now suppose that you've defined your SampleX and your template, maybe many of them, and you're ready to run on hardware. What do? Well, this is why we've defined the executor primitive. It accepts natively as input SampleX objects and their corresponding template objects. You actually don't need to use Samplematic at all with the executor. You can just feed it circuits without SampleXs if you want to. But I'm going to invite you to think about the executor in the following terms. I would like you to try to think about it as a tensor manipulator, right? In the same way that you think about the backends of tools like PyTorch or TensorFlow being flows of tensors through some tensor manipulator graph. And if you have a parametric quantum circuit, you can think about it as a tensor manipulator. So suppose it has 70 input parameters. And suppose it has 1 classical register with 130 bits. So it's a tensor manipulator that expects a 1D tensor of floats of size 70, and that promises to return a 1D bit array of size 130. And maybe you have a second circuit that accepts a 1D tensor of 300 parameter values and returns, because it has 2 classical registers, 2 arrays, 1 bit array of length 3 and 1 bit array of length 120. Fundamental to IBM QPUs at the execution level is the concept of a shot loop. A shot loop is the basic building block of execution on IBM QPUs. And we can also think about shot loops as a tensor manipulation model. Inside of a shot loop, you can make many clones of a single parametric circuit. And you can also add clones of a different parametric circuit. And so you can add a bunch of clones of a bunch of parametric circuits. And in this picture, under the tensor picture, what you're sort of doing is augmenting the dimensions of your tensors. So the shot loop, instead of expecting a vector of length 70 for your first circuit, it expects a tensor of shape 5070 because you happen to have 50 clones of your first circuit inside of the shot loop. And then we also have, in this example, 10 clones of the second circuit inside of our shot loop. And the corresponding output arrays have also been augmented in dimension. So instead of getting a bit vector of length 130, we add a dimension for all of the clones inside the shot loop, and we add another dimension for all of the shots that we're rastering over. Now inside of a shot loop, what is happening is you execute the first clone of the first circuit, then the second clone of the first circuit, then the third clone of the first circuit all the way, and then you execute the first clone of the second circuit, the second clone of the second circuit all the way. You get through all of your work. Now you've done one shot of every circuit. You loop back to the beginning, and you do that for, in this case, 64 shots. So that's what a shot loop is. We saw in the previous slide how the Samplex object is a tensor I/O model. And so what Executor promises to do is stitch together your tensor manipulators in this way. So it promises to take the output parameter values of your Samplex object and feed it directly into the shot loop for the corresponding circuit. And if the Samplex happens to return any other tensor values that are not parameter values, those skirt around the shot loop and get directly returned to the user. The Samplex, of course, also has input parameters. So those need to go as inputs to the Samplex query. And the Samplex also has some number of randomizations implicit in the job. And so this also augments the size of the thing. Typically, users in these powerful randomization-based mitigation methods cannot fit all of their work into a single shot loop, but you want to fit it all into one job. For this reason, there's a notion of a runtime batch loop inside the runtime environment right next to the QPU. Each iteration of the runtime batch loop has exactly one shot loop inside of the executor. And the job of the runtime batch loop is to take all of the input tensors that the user has given to the executor, chunk off a little piece that it knows is going to fit into one shot loop, feed it to the shot loop, execute, and then at the output boundary of the batch loop, it's going to stitch together all the results and pretend that it all came from a single execution, right? And so you get to preserve the tensor input-output model that the executor defines. The executor also has some metadata that tells you the timing information of each of these shot loops. So this is the sort of programming interface for how you create one of these pictures that I've been describing. It's not very complicated. So Qiskit IBM Runtime, and to be very precise, currently a feature branch of Qiskit IBM Runtime, so you need to check out a branch called Executor Preview to get these objects. But if you do, inside of Qiskit IBM Runtime, there's a new object called a quantum program, and there's also the executor primitive. And what you do is you instantiate a quantum program, and you say shots equals 64 or something, and you give it a bunch of noise models, which all of the items in the quantum program are going to be able to share. And then to the quantum program, you append a bunch of items. And each item corresponds to sort of a horizontal slice of this process that I've just described. So in this particular example, I have one quantum program item, which is a Samplex template pair, and I have another quantum program item, which is just a parametric circuit. And so in the first case, I need to give the template the Samplex and also the input arguments to the Samplex. And then in the second program item, I'm just giving it the parametric circuit and a big array of parameter values that I want to sweep through during my execution. And then I've built up my quantum program in some way, and I submit it to the, I give it to the executor, I call run, and I get a job object, just like the other primitives. Very similar to the sampler v2, the executor has broadcasting semantics, which is a powerful mechanism to let you sweep over large numbers of configurations of your experiment. And so let's imagine a situation where one of the items inside of our quantum program is a samplex item. And let's suppose that the samplex wants as input 3 different tensors. Let's suppose that it wants some input parameter values for the base circuit. Let's suppose it also wants a basis shape array. And let's suppose that it wants some scaling values to apply to your noise models during noise injection. All right? So each of these tensors is going to have a shape. And the convention that we use is that the trailing, or the last elements of the shape of these tensors is the shape that the samplex itself wants to consume. Like, so for example, if the samplex wants some parameter values to plug into your initial base circuit, it's just going to be a 1D vector of parameter values, 300 parameters or something like that. On top of that, we can specify, a multi-dimensional sweep of parameter values. So in this case, I have a sweep of parameter vectors, which is shape 1, 130, right? So 30 different parameter sets. And we can do the same thing for basis changes, except this time, instead of sweeping it along the third axis, I'm going to sweep it along the 10 axis with 10 different basis changes. And then similarly, I have a bunch of noise scales that I want to sweep. And so I'm going to do 3 noise model scales, and I'm going to put that on my first axis. And so what I can expect from the executor is to use standard NumPy broadcasting conventions to determine the output shape of my bit arrays. So in this example, my return data array is going to have shape 3, 10, 30, because that's the broadcasted shape of my program item. And then it's also going to have an axis for shots and and an axis for bits in my classical register. And in this example, we're sort of doing an outer product, right? So we're doing all of our sweeps along separate axes. If for some reason you needed to sweep your basis changes simultaneously with your parameter values, well, you would just put those on the same axis, and then they would sweep together in this convention. It's just like the sampler v2 if you use those broadcasting semantics. And it should be emphasized that the executor having samplexes in there does not slow you down. And we can demonstrate this by looking at CLOPS, so cycle layer operations per second. This is an execution benchmark that tells you how fast you can execute circuits, and it does this by defining a very specific payload and measuring the steady state execution speed of the thing. This benchmark, you construct a 100 by 100 circuit where each of your layers has 5 gates in it, 5 single qubit gates on each qubit, and then a bunch of entangling layers that are ISA compatible. And then we're going to demand 5,000 randomizations of this 100 by 100 circuit, and we're going to demand 100 shots per randomization, and we're going to start a timer at the end of the first shot loop, and we're going to stop the timer at the end of the last shot loop. We're going to look at that duration, and we're going to count how many layers of this workflow we were able to execute in that and give it in units of layers per second. And we can do this benchmark in both the sampler and the executor. It's maybe too small to read. I'll tell you what's going on. So in the sampler, we construct a pub where we give it the 100 by 100 circuit and all the parameter values that it requires. In the executor, we need to first take our circuit, box it up, construct a samplex, and then we give that samplex to a quantum program for execution. Then we're going to send it to a backend inside of a session. So in the sampler case, we need to configure the options to do 5,000 twirls of the base circuit at 100 shots per twirl. And in the executor example, we're going to give it the quantum program to run. And then both of these primitives inside of their job metadata will give you certain timing characteristics. And these timing characteristics are sufficient to compute the CLOPS, which is just a simple division layers per second. And you can see that in both examples, we are saturating the performance of this particular device at something like 230,000 layer operations per second. Okay, so we have run our job, we have our data, it's time to post-process. I won't talk too much about this, I'll just tell you that there is data, that it is tensor valued, and that for every item in your quantum program, you are going to get one mapping object, and that mapping object is going to contain a named tensor for everything you expect to get out, right? And it's also worth pointing out that before you even run your experiment, it's very easy to determine exactly the types and shapes of things that you'll get out of the thing, because all of these broadcasting semantics are sort of deterministic and introspectable before you execute. So in this example that we've been going on with, we have two program items, so we're going to get data 0 and we're going to get data 1. Data 0 is going to contain the data that came from the QPU, so bits from our QPU inside of the mesh thing, because that's what we named our classical register. It's also going to give us some measurement flip data because we've chosen to do measurement twirling in this example. So that didn't come from the QPU, that came from the samplex. The first quantum program item had no samplex, it was just a regular parametric circuit, and so we're just going to get one tensor for every classical register that was in the circuit. And these are expressed in Boolean arrays, NumPy arrays. And so with that, I've told you everything I would like to tell you about an introduction to Samplematic and the executor. This QR code will link you to the executor and Samplematic documentation on our website. And with that, I am very happy to invite Max Rozmanik to the stage to continue with some applications and tools built on top of this framework. Thank you.